In this lecture, I will go over the basics on horizontal asymptotes. In the previous lectures, I just looked at the mechanics of them and how to figure them out from looking at the polynomial. But here I'll go into some of the mathematics behind horizontal asymptotes. The basic thing behind horizontal asymptotes is that the horizontal asymptote represents or is the long-term behavior of a function. In this case, we're talking about rational functions, but it is a long-term behavior. And by that, if you look at the independent variable x and you watch how the function behaves as x goes to either plus infinity or as x goes towards minus infinity, what happens to the function? Now, some functions never settle down. For example, I might have a sine wave. And as x increases, if this is the sine of x, you don't have to know what that is yet, but some of you might, so you're kind of wondering. Sine of x is a function, and it goes like this, and it never settles down. It just keeps oscillating, plus, minus. And then also, if I go this way, again, plus 1, minus 1, plus 1, minus 1. It never settles down. However, these rational functions do settle down. And there's certain rules for figuring out what they do and finding the value that they asymptotically approach. So the value of the function, in this case it's going to be a polynomial. So we want to know the value that the polynomial p of x approaches. It doesn't have to get there, it just has to get close enough to it. That the value that p of x approaches, okay, there's supposed to be O's and A, then an A, approaches as x goes to plus and minus infinity. We're not talking about the polynomial, we're talking about a rational function. Okay, so the first thing you have to do is get an understanding that as x goes to either plus infinity or minus infinity, the simplest rational function, 1 over x, will go to 0. That's the basis for understanding how these work. Sort of figure that out. Let's just make a table of values. So here's r of x, and it equals 1 over x. And now I'm going to look at all the values as x gets larger and larger. So when x is 1, this function, r of x, just has the value 1. If x is 10, it's 1 over 10, so it's 0.1. If it's 100, it's 0.01. If it's 1,000, it's 0.001. And you could continue like this. Here, let's let it be 1,000,000. And that's going to be, okay? So the bigger x gets, as this gets bigger, the overall function gets smaller. It goes towards 0. Okay, it can never go negative. As x gets bigger and bigger, there's nothing to change its sign, so this thing can never go negative. It can never really get to 0, but it gets closer and closer and closer to 0. If I graph that, okay, here's 1 and 1, so it's here. So now the function's at 10, it's down to 0.1. Of course, I'd have to use logarithmic scale. And as I plot this, it goes down and down and down. It's swooping out closer and closer to the line y equals 0, and that's its asymptote. The same thing holds if x goes to minus infinity. Get a pencil here. So here's the x, and here's 1 over x. So if x is minus 1, this is minus 1. If x is minus 10, it's minus 0.1. Minus 100, it's negative 0.01, and this trend also continues. So you can see the number is getting closer and closer to 0. It's not changing sign, so it's not crossing over that axis. Although there's nothing to prevent it from doing it, it just doesn't do it. So we can write this in the following notation. As x approaches, that's what the arrow means, approaches plus or minus infinity, this function r of x, which is just 1 over x, approaches 0. So this is going out towards infinity. The functions going towards 0. This would also hold true, of course, if we had this function. So if I plotted my values, here's x, and here's 1 over x squared. Alright, when it's 1, it's going to be 1, it'll be 10. So that'd be 1 over 10 squared, 1 over 100, 0.01. It's doing the same thing as it did before, right? It's, if this is 10 to the, say, 12th, this would be 10 to the minus 24. So again, the function is approaching 0. As the denominator gets larger, the overall function gets very small. And so if you have those two understood, and if you need to plot out or calculate a whole bunch of points and plot them out, do that a couple times till you have that understood. That's fundamental. Now, let's look at something that's just a little bit more complicated. If I have, I need the pen. If I have 3x squared as x gets larger and larger, which number gets bigger, shall we say faster? This becomes faster because it's x cubed. And even though this is getting bigger, this will get bigger much faster and swamp out the x squared, and the whole result will be this will go to 0 as well. And you can plot some points or calculate some points to convince yourself of that. Well, there's a principle behind this, and it has to do with the degree of the numerator and the degree of the denominator. As long as the degree of the numerator, which is here, is less than the degree of the denominator, then the horizontal asymptote is 0, y equals 0. So I'll write that like this. If the degree of p, that's the numerator, is less than the degree of q, then the horizontal asymptote is y equals 0. Now let's look what happens when the degrees of the numerator and the degrees of the denominator are the same. Okay, here's an example. Say we have 6x cubed divided by 2x cubed minus 4. Of course you could simplify it, but that's not the point. Right. Now in this case, the degree of the numerator is 3 and the degree of the denominator is 3, so we can't use the previous rule. Remember, the previous rule is if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. So let's see what happens in this case. So what I do now is I work out the long division. So 6x cubed divided by 2x cubed minus 4. Well, I get a 3 up here, so that's 3 times 2, so 6x cubed minus 12. And subtracting gives me a 12. Now I don't go any further in my division, right, because I have this, I have a term that's less than the degree of what I'm dividing by. So this is where I stop. So now let's write this out. This would be 3 plus 12 over 2x cubed minus 4. I just worked out the division and then put the remainder over the divisor. Now look what I have. I have a rational function here, and the degree is 0 in the numerator in this case, and the degree is 3 in the denominator. When I'm done, I will have a rational function that looks like this. All right. The numerator will have the degree of the numerator will be smaller than the degree of the denominator. It might not be 1 and 0 and 3, but it's going to be smaller anyway. Okay, so now look at the long-term behavior of this function. As x goes to infinity, I'm working at two terms. One is a 3, which is going to stay a 3 no matter what, and then I have this other 12 over 2x cubed minus 4. All right. By a previous rule, this goes to 0 because the degree of the numerator is 0 and the degree of the denominator is 3. Nothing happens to 3, it stays the same. Therefore, the horizontal asymptote, for this case, is y equals 3. The general rule is that it equals this answer. But how did I find that answer? What I did was look at what number would turn the denominator, this 2, into a 6, because the degrees are the same, so all you're worrying about are the coefficients. What do I do to change the 2 into a 6? Well, obviously, I multiply by 6 over 2. And the horizontal asymptote is often written as this because it's the ratio of these leading coefficients. So you can use this rule. For example, if I don't have the pencil, if I had 20x to the 9th divided by, I want to say 6x to the 9th and plus 2x squared minus 4, and I want to find the horizontal asymptote. The horizontal asymptote is just a fraction made of this coefficient and this coefficient. So the horizontal asymptote is y equals 20 divided by 6, which is 3.5. If the rational function has this form, let's say it's 45x to the 5th divided by 9x to the 5th minus 12, then the horizontal asymptote is just a fraction made out of those two numbers. So the horizontal asymptote is 45 divided by 9, that's 5. Now we'll do a couple just for practice. If I have 19x to the 26th divided by 3x to the 30th plus 4, what is the horizontal asymptote? We go up here and look at the degree of this. Of the numerator is 26, the degree of the denominator is 30. Right? So in this case, y equals 0 is a horizontal asymptote. Let's say they were equal. If I had 12x to the 30th divided by 3x to the 30th plus 4. Okay, so now I look and notice that the degrees are the same. So the horizontal asymptote is y equals 12 over 3, which is 4. Now the following case you're not responsible for in this class, but it helps to look at it so that you get a better understanding of these asymptotes. Let's say, okay, for review, if the degree of the numerator p is less than the degree of the denominator, which I'm calling q, then the horizontal asymptote is y equals 0. If the degree of p is equal to the degree of q, then the horizontal asymptote is y equals, I'm going to say an over bn, because I will write the rational function like this. I'm writing out the polynomials. So I have an x to the n in the numerator, an minus 1, x to the n minus 1, just in the general form, counting down, okay, to a0. And now in the denominator I can't use a's again, so I'll use b's for the coefficient. But remember, I'll use n because the degree was the same. I'm counting down to b to the 0. Okay, so the horizontal asymptote is a fraction made out of the leading coefficients. And I'm going to look now at the third case, and in this third case, the degree of p is equal to the degree of q plus 1. It's just 1 greater. So if the degree, for example, of q is, say, 5, then the degree of the denominator is 6. So the rational function that I'm going to use for an example will have, let's say, 8 x to the 6 minus 4 in the numerator, and in the denominator 2 x to the 5th minus 6. Okay, so the degree of the numerator is 6, which is 1 greater than the degree of the denominator, which is 5. So like I did for the example, when they were equal, I carry out the long division. So 8x to the 6 minus 4, and I divide that by the 2x to the 5th minus 6. So the first term I'm going to get up here is 4x. I can carry the rest of this out. 8x to the 6th minus 24x. Now I'm going to subtract, so I'd have 24x minus 4 would be my problem, and I'm done because this degree is less than the degree of the divisor, so I stop. So I would write this function as 4x plus 24x minus 4 divided by 2x to the 5th minus 6th. Well, this last term here is a rational function. The degree of the numerator is 1. The degree of the denominator is 5. So as x goes to infinity, this goes to 0, and it doesn't count. But I'm left with 4x. Although it goes to, of course, as x goes to infinity, this gets very, very large. It doesn't go to 0, and it doesn't go to any value. Instead, what that is a straight line. I'll have a better graph in a minute, but I'm going to show it to you like this. So what you would have is you could draw in this asymptote, but it's not going to be horizontal. Instead, it's going to be slanted, and it's called a slant asymptote. In this case, it would look like a line with a slope of 4. Then the function, as x goes to infinity, let's say the function is doing something like this. As x goes to infinity, it will asymptotically approach that line. You see how it's a slant asymptote? Perhaps a point down here would go and do something like this. So when the degree of the numerator is 1 greater than the degree of the denominator, then the asymptote is a slanted line. It's called a slant asymptote, and the function starts to approach it. If the difference is 2, then of course when you divide out, you're going to have a quadratic, and the function will then start approaching that. But so the only two we're considering in this case again is if the degrees are equal, in which case you make a fraction, or if degree of p is less than the degree of q, and that also is a horizontal asymptote of y equals 0. So let's look now at the graph of this particular function and see the slant asymptote. So here's this graph, and you can see the degree is 6 in the numerator, 5 in the denominator. Division will give you the line 4x, y equal 4x, and that is the asymptote, and it's a slant asymptote.